Today's lesson will be an introduction to calorimetry. Unit A in this course is all about thermochemistry. If chemistry is the study of chemical reactions, thermochemistry studies the energy changes that occur during chemical reactions. When we study energy changes in thermochemistry, we will do our best to use isolated systems, carefully designed experiments, and use precise measurements. The first equation that we will be using in thermochemistry is Q equals mc delta T, which you have learned before. The Q is the amount of energy in joules, the mass is measured in grams, and the temperature change is in degrees Celsius. The small c is the specific heat capacity, which is different for each substance. Your data booklet contains information about specific heat capacities. If a specific heat capacity is required that isn't in the data booklet, you will be given the value in the question. Mass, specific heat capacity, and temperature change all affect the total amount of energy released or taken in. For example, a bathtub and a teacup of water have contents with the same specific heat capacity. If you want to heat them up, it will take considerably less energy to heat the teacup of water because there is a lower mass of water in the teacup. In this first example, you are given a volume of water and a temperature change. Recall from previous science courses that 1 milliliter of water is equal to 1 gram of water, so you can use 115 grams for the mass. You will use the specific heat capacity of water and the temperature change given. Multiplying these three values will give you the change in thermal energy in joules, and then you can get the value of kilojoules by dividing by 1,000. It is very common to adjust the value to kilojoules so that you can have the correct number of significant digits without using scientific notation. If there is an ionic solution dissolved in water, it is common to use the specific heat capacity of water, even if the water is not pure. While the common units for specific heat capacity are joules per gram degrees Celsius, sometimes you will get questions that have liters or kilograms instead of grams. When this happens, you will want to use the amount of the substance in the same unit. Your answer may be in joules or kilojoules, depending on the units given, so pay attention to the units for the specific heat capacity. In this example, you are given the amount of energy absorbed by ethanol and asked to solve for the mass of ethanol. The equation can be rearranged to allow you to solve for m. Pay attention to the units here. Since kilojoules were used instead of joules, the answer ends up being kilograms instead of grams. As questions get more complicated, be careful to ensure that each value in Q equals mc delta T correspond to the same substance. Calorimeters are devices that are used to calculate energy changes. In our lab, it will be common to use polystyrene cups to create an isolated system. These classroom calorimeters are the closest approximation we are able to make without using expensive lab equipment. If you go on to university chemistry, you will be able to use real bomb calorimeters. In our experiments, you will dissolve a chemical in the water of the calorimeter, and the energy will transfer from the system, the chemical, to the surroundings, the water. This energy transfer will result in a temperature change of the water. Here is an image of what a calorimeter may look like in our labs. It is very helpful to understand that there are two systems occurring. The chemical system has to do with the chemical reactions, reactants, and products, and the calorimeter is the surrounding water that will change temperature when it takes in or gives energy to the chemical system. This diagram shows how the chemical energy lost or gained by the chemical system goes into the water. In reality, the chemical system is not one tidy block, but it will likely be mixed right in with the water. Energy is either absorbed from the water or released to the water. We will typically measure the change in temperature of this water, and so we will use the specific heat capacity of water, and this information will allow us to calculate information about the chemical system. There are several assumptions that we will make in performing our experiments and calculations with calorimeters. The first is that our calorimeter is perfectly isolated. Even though some energy will escape, we will assume that it all remains in the system. We will also use the specific heat capacity of water given in the data booklet for all temperatures of water. In reality, this value changes slightly as temperature increases. Don't overcomplicate things for yourself. In Chem 30, it is okay to use this value only. Another assumption we will make is that the specific heat capacity of dilute solutions is the same as that for water. In reality, dissolving ions in water will result in a slight change to the specific heat capacity. We will also assume that every bit of energy released by the system will go to the water, or that every bit of energy absorbed by the system is taken from the water. This brings us to the end of our lesson for today.